On to example 11. We are given some information about a radioactive source in the table, and we're given the activity, we're given the energy absorbed per kilogram, and the radiation weighting factor. And what we've been asked to work out is the absorbed dose and the equivalent dose. So just as usual, gather together the information that you've been given, and then you can decide what to do with it. We've been given the activity 500 megabecquerels. Now we're not going to need it, but I'll make a note of it anyway just to show you the process. So we've got that activity. Now we've been given the energy absorbed per kilogram. Energy absorbed per kilogram, energy divided by mass, you would hopefully recognize as being the absorbed dose, which we give the symbol D. So that's the trick really in this question, that we're actually given the absorbed dose D, which is 0.2 microjoules per kilogram. And following the formula, energy divided by mass, that is the same as 0.2 micrograys. That's just the definition of the gray. And the third piece of information we've got here is WR, the radiation weighting factor of 10. So we can go ahead and work out the absorbed dose. Well, we've already done the absorbed dose, which is 0.2 micrograys. And the last piece that I need really is the equivalent dose, H, equals D times WR, which would be 0.2 multiplied by 10, which gives me 2. Now, units for this will be sieverts or microsieverts. Now, because I've used micrograys, then I will have microsieverts. If you want, you could have done 0.2 times 10 to the power of minus 6 times that by 10, and you would get your answer in sieverts. But if you notice that the question gives you an answer in micrograys and microsieverts, so you're better to leave this one in microsieverts. So which option are we looking at? So option A, if you've got, this is page 12, option A, absorbed dose 0.2 micrograys and equivalent dose 2 microsieverts. So option A is the correct for this multiple choice. So that's that one. On to number 12. Human tissue can be damaged by exposure to radiation. Which of the following factors does the risk of biological harm depend? Factor number 1 is the absorbed dose. So factor number 1, absorbed dose D, will have an impact on the risk of biological harm. Factor number 2, the type of radiation, so that can be alpha, beta or gamma, or it could be fast neutrons or protons, proton beam therapy. So the type of radiation, which we have the radiation weighting factor, for example alpha having a factor of 20, that will also have an effect on the biological damage. And then for number 3, we've got the type of tissue. Now we don't really do much on the type of tissue in the National 5 course, but you need to know that basically, yes, some tissues are more sensitive to radiation damage than others, so that one also will have an effect. So for example, your digestive system is roughly 10 times more sensitive to a particular dose, equivalent dose of radiation, than say your skin. So basically all three of these, 1 and 2 and 3, and that is option E on your list. Okay, so that brings us on to example 13, which is on page 13 of the notes. So in this one, a technician is handling an alpha emitting source and estimates that his hand received an absorbed dose, so again D, absorbed dose of 5 times 10 to the power of minus 5 grays. the mass of the technician's hand is 500 grams. And we've been asked to work out the equivalent dose and the total energy. So part A, the total energy. So for part A, we can use the definition of absorbed dose, D equals E divided by M. You're rearranging that for E equals D times M. So the energy is the dose times the mass. Now the technician's hand is 500 grams, but a common mistake is that a student will just go ahead and put the number straight in here and leave the mass as 500. That would be 500 kilograms, which is not correct. So this is 0.5 kilograms. That's because the dose is measured in joules per kilogram, so the mass has to be in kilograms. So 5 times 10 to the minus 5 multiplied by 0.5. So that'll give you 2.5 times 10 to the minus 5. The unit for energy is joule. So that's part A. Part B asks you to use the information from the table to calculate the equivalent dose received by his hand. So the only piece of information you need from that table is the WR. It's alpha emitting, so the WR radiation weighting factor that we use is 20. And then we use the equation that the equivalent dose is equal to the absorbed dose multiplied by the radiation weighting factor. So then we use the dose that we have been given. So the dose was 5 times 10 to the minus 5 grays. So don't be fooled, don't try to use your energy, you need to use the dose in this equation. You multiply that by 20, which will give you 100 times 10 to the power of minus 5 sieverts. Now you could rewrite that as 1 times 10 to the minus 3 sievert. Also, you don't have to, you could leave it as 100 times 10 to the minus 5 sieverts. But if you do that, then you might also recognise that that is 1 millisievert. So 1 millisievert is quite a small dose of radiation, and whilst we're at it, something like 2000 millisieverts or two whole sieverts, that starts to get pretty dangerous. So 1 millisievert is not dangerous. Right, that's example 14. So then we're on to, so that was 13. Now we're on to example 14. So I numbered that one wrongly. That was example 13. So this is number 14. The oil industry uses radioactive sources to monitor the flow of liquids in pipes. We have a detection system attached to the outside of the pipe as shown. So the source used has an activity of 1.11 gigabecquerels. Explain what is meant by this statement. So activity equals number of decays per unit time. That's the definition of activity. So 1.11 gigabecquerels means 1.11 times 10 to the power of 9 disintegrations per second. So wherever you're asked to explain what a quantity like that means, you can go back to the formula and use that as your definition and provide your explanation from that. So it's just over 1 billion disintegrations per second. Next part. A sample of tissue exposed to this radiation receives an absorbed dose of 0.13 milligrays with a radiation weighting factor of 9. Calculate the equivalent dose. So we're given the absorbed dose, 0.13 milligrays, and the radiation weighting factor, WR, equals 9 for this. There's no units for the radiation weighting factor, it's just a scaling factor. And then we apply the formula H equals dWr. So that will be 0.13 milligrays multiplied by 9. (1.17 millisieverts). So 1.17 millisieverts, and I probably want to stick with two significant figures, so I'll go for 1.2 millisieverts. I haven't left myself much space there. Last part, C, asks what is the purpose of the cage. So the purpose of the cage ensures that the human operator can't get too close to the radioactive source. And increasing the distance like this reduces the dose. And it does that quite dramatically, so if you go twice as far away, you actually get only 1/4 of the dose.